first, second row, whatever. I think students get more out of a lecture if they're closer to the lecturer. It's more like a conversation. And that's how we evolved communicating with face-to-face after we read the language thousands, tens of thousands, hundreds of thousands of years ago. We don't need a special coupon to sit in the front. You're going to have a hard time because there's something blocking your view, not that I'm going to look at. So this is a 3-credit course. You should not be worried about this course, even though it's a physics course, because, well, my view of the course is that, I guess we can start the video now. The purpose of this course is to educate you, to tell you something about science and more particularly about physics. I'm in fact going to try to tell you everything that I know about science, but without equations. And I don't really want the administration to know that I might be able to, that I know so little that I could teach it in one semester, but especially in a 102 class. But I think the concepts of science, the main concepts of science, are sufficiently simple that I can understand them and explain them, and you can understand them and explain them to your friends and so forth. The second purpose of the course is to give you 3 credits and some sort of a decent grade so that you're on your way to keeping your lottery scholarship or graduating. And I take that seriously. In fact, there are always random errors of grading. And so my policy is simply to give everybody a higher grade than the person thinks he or she ought to get. So I just sort of aim high, and I think that's right. I'll just mention parenthetically that the chairman of the Federal Reserve Bank, Janet Yellen, who's done a marvelous job, I think, recently said that people who graduate from college do better in life. Of course, you can imagine that that's true, but in fact it's significantly better. They earn significantly more money, have better health care, live longer, and so forth. So I think hard-nosed grading is anti-social. All right, now today I'm going to tell you the story of the beginning of the universe. This is a little bit like the Bible, except that I haven't actually read very much of the Bible, so especially the Old Testament. So I'm not really going to try to follow the Bible in any case. The story is very different, and it's extraordinarily amazing. In fact, it's fantastic. In fact, if Hollywood had made a movie of it, people would leave the theaters saying, well, that was interesting, but of course it can't be true. And we know something for sure about the beginning of the universe. This is a picture of the universe when it was 380,000 years old. This is a color map of the, false color map, I should say, of the cosmic microwave background. By the way, I want you to read 2 books for this course, and an important part of your education will be reading these books. These are good books. Physics and Technology for Future Presidents is something that will tell you a lot about about science, about physics, and about how, if you were president, or you become president, how you should think about some of these things. So, of course, it will be 20 or 30 years, and so your physics and science will change somewhat. But it's a good book. The first 3 minutes is probably the best book for the best popular book about physics ever written. Possibly the best popular book about science ever written. The author, Steven Weinberg, won the Nobel Prize for Physics in 1979. He wrote the book in 1977, so it's 40 years old. On the other hand, he was so smart that it's basically entirely correct. Just some of the numbers are a little off because of new discoveries in the past 40 years, especially the past 30, 20 years. He added an afterword, I think he called it, where he brings some of it up to date. But in this course, I'll bring you up to date from what that book says. Then there are various things on the web. Alan Booth is one of the people who invented inflation, which is one of the topics I'm going to explain to you today. And he has some videos on YouTube. I forgot to write YouTube. Now, his lectures, I think, well, look at them. If you like them, great. If you don't, well, don't watch them. All right, so let me say this. As I said, it's a picture of the universe when it was 380,000 years old. What you're seeing here is the radiation coming from all directions in space. And one of the amazing things about it is that all the radiation is essentially the same. It's the same to within 1 part in 100,000. So the universe, in other words, on large scales, is homogeneous. In other words, the temperature out there is the same as the temperature out there. And of course, when we're talking now about the universe when it was 380,000 years old, now it's 13,820,000,000 years old. So it's 8. And those photons, of course, are particles of light. I'll say more. By the way, ask questions at any time. I brought a little bit of candy, and I'll throw candy to any student who asks a question. Something that's happened to our educational system that's discouraged questions. I think it's basically underfunding. Too many kids in the same classroom, and students have been taught to be quiet. Well, you shouldn't be quiet. You should ask questions. And so I encourage that. Also, another purpose of a question is I may say something in a jargon phrase or forget to explain something. That's even more likely. You ask a question, you'll fix it. So that's what I'd ask of you. So what does this tell us? This tells us that the universe was homogeneous 380,000 years ago. When it was 380,000 years old, and that was nearly 14 billion years ago when it started, when our part of the universe started. is something awkward here. We don't know. The only part of the universe we know is what we see essentially on this screen. These photons have been traveling from 13 billion, or nearly 14 billion light years away in all directions toward the Earth in straight lines, essentially, for nearly 14 billion years. That's the universe as we know it. Sometimes we call it the visible universe, the known universe. I'm just going to call it the universe. But you should keep in mind, especially after you hear this lecture today, that will tell you, when I'll tell you the fantastic story of the beginning of the universe, that there could be a lot more out there. Susskind calls it the megaverse, which I think is the right term. Most scientists call it the multiverse. So there could be many other universes, either similar to ours or different from ours, way out there. And when I say way out there, I don't really know what I mean. It's a part of physics that's not yet understood, but you'll see why this could be true when I get a little bit further on. The temperature of each of those spots was the same to, as I said, to within 1 part in 100,000. So it was enormous uniformity. On the other hand, these spots, which have been coming to us from so far away, could not, in other words, these spots, in other words, if you look at that spot and that spot, they're really something like nearly 30 billion light years apart. So a light signal go from one to the other would take like 30 billion years. On the other hand, they were the same temperature, but the universe is only 380,000 years old. So how did they get to be in equilibrium? How did they get to be the same temperature? To within 1 part in 100,000. And the story I'm about to tell you will explain that. All right, let me get to. I think I'll give you a fanciful description. I'll try it out on you. Imagine that we have a space-time ship. And in fact, we can imagine that it's a big ship and it's the size of this room. We're all in it. And we can go through anywhere in space and time faster than the speed of light, and in fact, move at the speed of thought, which is faster than the speed of light. And so imagine that this space-time ship is protected by a shield that will protect us from the radiation that exists outside. When you get above the atmosphere, there's a lot of radiation, which our atmosphere protects us from. And as we go back in time, so imagine we turn this space-time machine on and go up above the clouds, out into space, and then go back in time. Back hundreds of years, thousands of years, and the one thing we can't do is we can't leave the spaceship and change anything. When you go back in time, I mean, nobody knows how to make a time machine. And in fact, I think it's pretty primitive also. But if we could make a time machine, the one thing we can't do is get outside the time machine and change something, because that essentially gets us into a logical contradiction, because we would have changed something, and then the future, the present would be different, but yet we know it isn't because we've lived it. And so we can't get outside the space-time ship, just go back and look outside. And in particular, if we go back to 1963, we can't stop the assassination of John Kennedy, or that of Lincoln in 1864, 5. The history major, 5, thank you. Or can we go back to 33 and stop the crucifixion? We can't do anything to change history. We can just observe and look out our very protective windows. And as we go back thousands of years, tens of thousands of years, say, before people invented language or religion or wars, and then further back more than 5 million years, more than 5 billion years, I should say, before the Earth and the Sun condensed out of the ashes of exploded stars. Go way, way back. We'll see, if we look out the window, we'll see that there are more stars in the vicinity. In other words, the universe is denser. In fact, it's denser because it's smaller or more compact. And then, as we go back, let me just go really quite far back. If we go back to this point, a little after 380,000 years after the start of the universe, that's a moment that I call transparency. Astronomers unfortunately call it recombination, which is kind of silly because what they're talking about is that at this point in time, the temperature of the universe dropped, became sufficiently cool, about 10,000 degrees, so that hydrogen atoms could be stable. And once they became stable, the universe became transparent to visible light. And that's why we can see what it looked like at 380,000 years. Before that, if we now drive our space-time ship back in time, before 380,000 years, we look out the window, all we see is white light, totally featureless, because photons can't go more than a fraction of an inch before they collide with an electron and scatter. And so we can't see anything. It's just, it's what people call a plasma. Now what I want to do is go way back. By the way, the first 3 minutes, of course, is, that's the title of Weinberg's book, and he describes what happens in the first 3 minutes. I want to go back to the Big Bang itself and before the Big Bang. Now, we pretty much understand the physics of the universe once it was about a nanosecond old, which is to say, 1 part in 1,000 million, 1,000 millionth of a second. When it was that old, it was cool enough so that we understand the physics. So when we drive our ship back before those times, what I'm going to tell you, it's not settled physics. It's the best theory we have. So I'll explain that to you, and in 20 years you may hear that I was wrong, or you may hear that there's been proof that this theory is pretty much right. It'll probably change in some way. Yes?
I just have one question before you moved on. So are the photons in this example expanding outwards like that?
The photons are coming, here. Photons, there's a bright spot in this plasma suddenly was cool enough so that the universe suddenly was cool enough so that it was transparent. The photons from that bright spot went in every direction.
Okay.
And since the universe was transparent, they've been going in straight lines unless they hit a star or, a planet or something.
Okay, and they'll just go on for as long as they need.
Yeah.
Okay, gotcha.
So let's see. One of the problems with the questions, of course, is it disturbs my chain of thought. At my age, that could be a problem.
Before the Big Bang?
Thank you. Right. So we want to go. We're going to drive the spaceship before the Big Bang and look out the window, and what do we see? Well, in fact, let's go back even a little bit more than just before the Big Bang. Let's go back a year or so before the Big Bang. We look outside, nothing. It's featureless, it's black, it's cold, it's empty. Now, it can't be just totally empty space because there are always fluctuations. Quantum mechanics, I'll try to explain something about quantum mechanics to you in this book. Quantum mechanics tells us that everything is always fluctuating. So there are fields out there that are fluctuating, but the fluctuations are so tiny you can't see them. You look out the window, black, dull, and you think, well, this is a pretty grim landscape. Not much is happening, not much is going to happen. I can't imagine anything happening. Well, our pilot knows where a spot in which the field, but the field is a term in physics for just something that depends upon space and time, varies with space and time. So we have a gravitational field. That's why if you drop something, it falls. Electromagnetic fields are what carry, light is an electromagnetic field. Radio transmissions are electromagnetic fields and so forth. And then there are also scalar fields. And we don't know a great deal about these scalar fields because the first discovery of a scalar, of an elementary particle of a scalar field was only in 2012. It was announced on the 4th of July by the European Center for Nuclear Research. It's called the Higgs boson, and it's very heavy for an elementary particle. It's about the mass of an atom of cesium. Anyway, back on track. Before the Big Bang, look out the window, nothing. But we know where to go. We know where there's a spot where there's going to be a huge fluctuation. Okay, so there's a random fluctuation. Most fluctuations are small. When fluctuations are large, quantum mechanics tells us the fluctuation has to be short. So, or typically it's short. So, actually, quantum mechanics doesn't tell us that it has to be short. It tells us that the lifetime of the fluctuation is inversely proportional to the size of the fluctuation, or bigger. So the lower limit of the fluctuation goes as inversely proportional to the size. So you can have, if you have a big fluctuation, it can last a very short time. But if you have a small fluctuation, that's really small, it can last a long, it in fact has to last a longer time. But all these times are very short though, because the constant of proportionality is Planck's constant, which is so small that I've forgotten what it is. It's of course well known. When I do calculations, I often set it equal to 1. So let me now tell you what basically happened there. There was a fluctuation. What we think happened there. This is not settled physics, but that's it. There was a fluctuation in the scalar field in a small spot. How small a spot? Well, we don't know. It was smaller than about 4 millimeters. But it could have been smaller than an atom. It could have been smaller than a nucleus. And in fact, Alan Guth thinks that it's much, much smaller. The spot was much smaller than a nucleus. But the fluctuation was enormously high. And so the scalar field got to a value that was just absurdly high. And at that value, the energy in the spot was huge. Now, there are generically two kinds of energy. There's the energy of what we call kinetic energy, and then there's potential energy. And energy is conserved. And I can illustrate that with this demo. I'm going to pull this ball back here, if I do it right. And this ball has, in effect, potential energy, which will be creates kinetic energy when I release it, because it will go down and the potential energy will drop. And then the ball nearest him will shoot out and will rise about as high as this ball is and stop. And when it stops, it will have the same potential energy as this ball. And when I release this ball, the potential energy turns into energy of motion, which is called kinetic energy. So, and if this demo were perfect, this would go on forever, apart from air resistance. But I think we're getting tired of it, so I'll just stop it there. So that's the idea. We have two kinds, basically, of energy. Energy of motion, kinetic energy, and potential energy. The energy of motion is basically how things are changing in time. The other energy has to do with fields and field energy. Now, there's something that we can demonstrate about this energy business, namely the energy of gravity. The field energy of gravity is actually negative. So in other words, if I drop this, it gets going faster. Why does it get going faster? Well, it gets going fast, of course, it gets going fast because the gravitational field pulls it down. But what about energy? Well, there must be less potential energy when the eraser hits the floor because there's so much kinetic energy. On the other hand, the gravitational field is bigger because we've taken the mass of the eraser and moved it closer to the Earth. So the mass of the Earth plus eraser is concentrated. Not a big effect, of course. But the point is that the gravitational field has potential energy and it's negative potential energy. That's important. All right, now let's get back to these fluctuations. About 100 years ago, Einstein published some of his final papers on general relativity, and the basic idea of general relativity is that you should be able to use any coordinate system to describe the laws of physics. And that when you change your coordinate system, the laws of physics should remain invariant. And that's a very abstract notion, but on the other hand, when you think about it, what it means is that the laws are what they are, and we can describe them any way we like, but there isn't any particular reference frame or coordinate system that's necessary, that we have to use. All right, this is very abstract. Let's just skip it and say this is the way it is. Now, what general relativity tells us is that the gravitational field is coupled to energy. And so when there's this fluctuation of the scalar field normally, because the energy, potential energy of the scalar field is all of a sudden huge in this tiny spot, the forces of that field force it down, would shoot the scalar field right back to its neutral value of zero potential energy, and just very, very quickly. However, general relativity says that the gravitational field is coupled to energy, so there's a sluggishness of the transition back to the zero value. And so that fluctuation lasts much longer than it would if there wasn't any gravity. The other thing is that I told you that gravity creates negative energy. In fact, it also creates, in that little spot, negative pressure. And the negative pressure is really fantastic. And according to the laws of Einstein's equations, by the way, Einstein's equations in general, there's 16 coupled nonlinear partial differential equations, nightmare. But when you apply Symmetry, the universe is homogeneous. Duh. It's the same in all directions. Duh. All of a sudden, the thing is so simple that you can do it in an elementary. Well, you need calculus, but it's pretty simple, and in fact, it's not much different from the description of things going up and down, falling in a gravitational field. But if I can get that in a simple form, I will in a later lecture. But now let's just say what happens. The field fluctuates randomly to a very high value. Gravity keeps it there longer than it would be there ordinarily. So you have a small spot of very high potential energy. Gravity then causes that spot to have negative pressure, and the spot, and then general relativity has that spot expand exponentially, unbelievably rapidly. It's the space that expands. It's not that particles are moving in space. It's that space itself expands. After all, Einstein's theory is a theory that treats space and time as kind of plastic, flexible things. And so here, space expands, and this tiny spot, in a tiny fraction of a second, expands so big that it's, let us say, more than, well, we don't really, you see, this is unsettled physics. I don't know how big the fluctuation was. I don't know how long it lasted. What I can tell you is the amount of the expansion. That spot expands by a factor of something like 10 to the 13th, maybe as much as 10 to the 26th. So it is all of a sudden, in a fraction of a second, less than a nanosecond, a thousandth of a millionth of a second. Less than that, it expands to a size that's about the size of our solar system. That's the minimum. It could be the size of a galaxy or much larger in an extraordinarily tiny fraction of a second. And then, in the next 380,000 years, it expands again and becomes what we see there, the whole known universe, and more, because after all, the known universe is just what we see coming at us now. In 100 years, there'll be more of it. It will be 100 light years bigger in each direction. I've left something out, and anybody have a question that might bring out what I left out? Or bring in what I left out?
I guess.
Yeah, all right.
Not really any more candy.
No. Yeah. Whoops.
Thank you. Anyway, so the fluctuation, you say, like, 'cause it starts out as just normal flat space.
Yeah.
So then would it be a fluctuation like if you took a rope and put a wave in there, like kind of just
Well,
like that?
yeah, you can think of it that way, but because if you think of the rope as the scalar field, then there was a fluctuation in the rope. Yeah.
Okay, got it.
Now, if it were an ordinary fluctuation and of a small size, then it would have been, as you say, it would sort of go up and then quickly down and dissipate.
Right.
All right. Instead, what happens is this is a huge fluctuation in a very tiny space, and so then gravity causes the rope effectively to become stiff, and so it doesn't go back quickly. It stays there. As long as it is a region of high potential energy, it expands like crazy.
Okay.
And moreover, the original energy of the spot was zero, say, or nearly zero. Then with the fluctuation, it was very intense, but very small, so the amount of energy was small. But then gravity expanded the space of the spot, and keeping the potential energy still high. So the result was, all of a sudden, there was an enormous amount of energy, and you'd say created from nothing, if you want, in a sense, but energy is still conserved because the gravitational field creates a corresponding amount of negative potential energy in the gravitational field. So the energy is conserved. Now, eventually, you have this spot, which was tiny, is now enormous. And almost no time has passed. It's an enormous spot at very high energy, potential energy. And then finally, time has come for the gravitational field to release that field, and it gets that down to its normal value, where the potential energy is zero. Then all that potential energy is converted into kinetic energy, or energy of motion, or what we call radiation. And so all of a sudden there's a flash. That's the Big Bang. And it occurs simultaneously throughout this enormous, this spot, which is sort of a gigaspot. It occurs instantaneously, and the temperatures are so hot that we don't understand the physics that describes them. And then the universe then continues to expand, but it's no longer expanding in this. The space is no longer expanding exponentially. Instead, the space is simply expanding rapidly. In fact, it's expanding as the square root of the time. In other words, when the time has increased by a factor of 9, the space stretches by a factor of 3. But so much so that by the time 380,000 years have passed, the universe has expanded the radius of the known universe is no more than 14 billion light years. It could be 100 billion. We don't know. We don't have any idea. So all this energy and mass, all the stuff in the universe was created, if you want, from negative gravitational potential energy by a random fluctuation, and the mechanism was general relativity and the nature of the scalar field and the way in which the potential of the scalar field varies with the field itself. We don't know what the scalar field is. We don't know if it's one or several. And as I said, we don't really understand the physics until something like a nanosecond after the Big Bang. After that, we can trace it pretty well, and the story is told very nicely in Weinberg's book. In fact, that's the best description that I know of. The numbers are a little bit wrong, but basically we got everything right, because he is not only a Nobel laureate, he's probably one of the greatest physicists of our time. By the one story is that after he won the Nobel Prize, he went to the dean at Harvard and asked for a raise. The dean said, "Well, Professor Weinberg, why do you think you deserve a raise?" And he said, "Well, I just won the Nobel Prize in physics." The dean said, "Yes, but we expect Harvard professors to win Nobel Prizes." And anyway, I wasn't in the room, so I don't know. I just heard this as a rumor. He also wanted to get his wife a job teaching. She's a lawyer. And so he eventually moved to the University of Texas, where he's at Austin. He's been there for 20 or 30 years now. Okay, let's see. What is it that I have to do? Yeah, is that a question? No. Okay. I saw a moving hand. I thought energy of motion of the hand would be a potential question. Okay, so in the Big Bang, as I said, the temperatures are so high that we don't understand the physics at those energies. But after about a nanosecond, we sort of do, and so I'll start telling you about that. It's particles of all kinds moving at very high speeds, photons, electrons. And now I have to tell you what the sort of particles are. They're what we call quarks. Among the ones that we know about are quarks, leptons, gluons. But the more important particles are particles we don't know about. And these are particles that don't interact much with light. And since our telescopes work on the basis of light, for the most part, we don't know a lot about this other kind of matter. And because it doesn't interact much with light, or not at all with light, we call it dark matter. It was discovered in about 1933 by Zwicky and somebody else. And then some woman also, whose name I've forgotten, but she died recently, I think, and in her obituary was mentioned that she was one of the people who discovered dark matter.
I think her first name was Vera.
What?
I think her first name was Vera or something.
Vera.
Yeah. I think so. I'm not
all right. I think you're right. Anyway, what Zwicky and others noticed was, if they looked out at a cluster of galaxies, say, they could estimate what the mass was of the galaxies. And then they could watch the galaxies move and they could tell how fast the galaxies were moving toward them or away from them by what's called a Doppler shift. I'll explain that later, but it's basically if the star is moving toward you, the frequencies of the light go up, or the light shifts in the blue direction. If it's moving away from you, it shifts in the red direction. And those changes in frequencies can be measured very accurately. So he knew roughly how fast these galaxies were moving, and he knew how much ordinary visible matter was in the cluster of galaxies, called the coma cluster. And there was a big discrepancy. And then he looked at other clusters of galaxies, same discrepancy. So he said, there's more matter out there we can't see if it's dark. I don't know if he used the term dark, but that's what he said. And most astronomers poo-pooed the idea. In fact, in faculty meetings, when I would say the word, the astronomers would make fun of me. But in fact, there's more and more evidence that is piled up that there's a lot, that Zwicky was right. And in fact, there's more dark matter than ordinary matter. So in this early universe at high temperatures, most of the radiation was these particles of dark matter that we don't understand. There's also something else that was discovered. And this was discovered basically in the last 20 years. And this is called dark energy. What has been discovered here is that it seems as though empty space has some energy, some potential energy that's causing space to expand the same way that the spot expanded into a gigaspot, but whereas the energy density in the spot was huge, the energy density in empty space is tiny. But still, it's causing space, the expansion of space to accelerate. And now I see I've skipped something. Ever since the Big Bang, the universe has been expanding. That is to say, space has been expanding. It expanded in as a square root. Then it started expanding linearly. And now space has expanded about by a factor of 1,000 since those photons were released. And in fact, that's why those photons had an energy of about an electron volt. That's the energy an electron gets when it goes through a potential difference of 1 volt, like a battery. They now have 1,000 times less energy, and they're microwave photons, whereas the original photons were optical photons. We see, perhaps blue photons. And so the universe has been expanding, but because of this dark energy, the expansion has been accelerating. And this acceleration has been noticeable for the last 4 billion years. We only noticed it in the last 20 years, but it's actually been, the energy density of the universe. If you ask, you look at a little cube of space, empty space at some, or just space at some point in time. Now, in fact now, you look at a bit of space, on average, 2/3 of the energy there is dark energy, which we don't understand. About 1/3 is matter. Of course, this is smoothing out the dark matter and stars and planets and everything. About 1/3 is matter. Of the matter, something like 85% is dark matter, 15% of the matter is visible matter. So it's really, I mean, what I'm telling you is we don't know anything, essentially. I'm telling you that the physics we know about is only about 15% of 1/3 of what is, of the energy in the universe. And the rest is dark matter, which we don't understand, and dark energy, which we don't understand. But we're good about, we're on the 4% that we understand, we're pretty good. Yeah.
I was just about to say, it's safe to say that we understand that.
I'm sorry, I'm a little hard of hearing. Could you shout?
I was just going to say, it's safe to say that we only understand about 5% of the universe.
Yeah. Yeah, 5%, that's even generous. It might only be 4. But we're trying, and progress is being made. Unfortunately, the funding of science in this country has been dropping for 50 years. Anyway, I could talk all day. My wife will tell you that. But we're already at the end of the hour, so I should let you go. I don't want you to make you late for other classes. But I'll go on with this fantastic story on Thursday, and I may put some of my notes. I'll put some of my notes online at some point. I don't know if they'll be up by Thursday. Yeah.
Can dark matter interact with physical matter at all, or you don't know?
That's a great question. Wow. That's a great question. People have been trying now for decades to detect dark matter, and they haven't succeeded. And so it's clear that the interaction of dark matter with ordinary matter is extraordinarily weak. And we just don't know if it's zero or just very, very weak. We have a group in the physics department that's trying to detect it, and they just haven't gotten there yet. And there are other groups all over the world. There's one group that claims they've done it, a group in Italy called DAMA. But they may not be right. All right, I better stop now, otherwise.
Thank you.
See you Thursday.
Thursday.